That's actually kind of genius. I think I did something wrong. I have stolen some code now. I've been made a fool again. Oh yeah. Einsteinian relativistic surface. It's swimming. What have I done? It's a tree geyser. Sure, we don't want to sit on it. Oh. That was really satisfying. It just kind of flows. Hello, everybody. Hello, and welcome to part 2 of me trying to build an infinite tree generator. So if you haven't seen part 1, definitely go ahead and check it out. Right now we're on leaves. We're trying to figure out how to build some leaves here procedurally. And I don't even know how we're going to do this, honestly. So again, if you haven't seen part 1, well, not when we did, you know, the branch structure. Oh, what the heck. We did the branch structure with just the branches and fractaling out like this. And that worked pretty well, but now what we need to do is every time every time a branch terminates, we need to put a leaf there, or several leaves, I don't know. But leaves are kind of, you know, often their own sort of fractal. So I'm really not sure completely how we're going to generate those because it's just, you know, different from the branch structure. It's like the main branches of the tree are its own fractal, and then the leaves are its own completely separate type of fractal. Kind of. But, you know, I don't even know how we're going to generate this. I'm thinking, I have a few ideas. The first one is maybe to just set out a line like this, and we'll have kind of different functions in the X, Y, and Z plane to give the leaf some shape, like this. Or you can set a different function to give the leaf a different shape, like maybe something like this. And then what you do is you take this and you flip it and just do the same thing on the other side to make the other side of the leaf. So then you go over here and, you know, like that. And then you got a leaf. And so we can take different, like, samples of points along the different parts of the leaf like this, as if, you know, the leaf growing is like a timeline. And then that's what we'll do. We'll just kind of take different points in the leaf and, like, connect them like that with some extra lines to give it that other structure inside of it. You know, I don't know. I'm not a biologist, okay? I don't know that much about leaves. I'm just going off the top of my head what my preconceptions about leaves are. We're just gonna bulldoze our way through here. We're gonna brute force it, like all good coders do. Another thing I was thinking is maybe like Bezier curves. I don't even really, what even is a Bezier curve though? Like mathematically, how do you define a Bezier curve? You know, I need to look that up right now because I've never studied that. Let's pull that up. Bezier curve. A parametric curve uses computer graphics and related fields. Wait, you can generalize them to higher dimensions to form Bezier surfaces? So this is kind of cool. It's something I've never really dived into before. So you've got different degrees of Bezier curves. So you've got linear curves with 2 points. It just goes straight there. And then you've got quadratic curves with 3 points. So you've got one point that goes from point 0 to 1, and then another one that goes from point 1 to 2, and then your final point goes between those points as it's traveling, and they're all doing it linearly, and so it ends up making this curve shape. That's actually kind of genius. That's pretty cool. And then for higher order curves, you just add more points, and there's more lines going between each other before the final point goes between that one, and by doing that, you can make ever more complex curves. That's insane. Okay, I do think this would be really useful for making different kinds of leaves though. So if we can figure out how to define these different points in space and then draw lines in the correct positions to form the Bezier curve, you know, depending on how we move around the points, we could probably use that to design, you know, custom leaves in real time. Maybe? I'm not sure. We'll see. I just need to figure out how to actually work the math for these. Okay, so I think I'm starting to understand this just a tiny bit from reading this Wikipedia page. So it looks like for any given Bezier curve of any sort of degree, it's defined by a bunch of polynomial terms, and the number depends on the order of the Bezier curve. So this is the general definition right here for it, where I was a little bit confused what these stacked variables are in the parentheses here, but it looks like it's a binomial coefficient. I don't know what that is, but apparently you get it from doing this division of factorials down here. And then basically, if you have a Bezier curve of degree n, you find all of the terms in the polynomial through this, and then sum them all up. That's your function that you plug t into to get all the points along the curve. I think that's how it works. Of course, I don't know anything about how they derived this. It would be pretty interesting to find that out, but just from this, maybe I can use that to run some tests in Unity and try to build some myself. But I think before I do that, I'm gonna start with these lower order Bezier curves explicitly, like these linear ones and the quadratic ones. Jeez. We'll start with those ones. and then maybe we'll move on to the general definition for them. So let's go ahead and do that. I've just been staring at this page for the last hour trying to figure out what's going on here. But also this is saying that it's using distinct points in the equation for the curve. I wonder if we can just replace those with like vector 2's when converting this into C#. For unity? Maybe, we'll see. Because it does say for P1 minus P0, it represents the displacement vector from the start point to the end point. So maybe it actually will work. I don't know, we'll see. We'll just do some experiments and see what happens from there. So let's open back up our tree generator project. Okay, so what we're gonna do first is start with updating this line in update to make sure that we can get a continuously drawing line that updates in real time. Well, it looks like that didn't work. Wait a minute. Oops, we're missing something. There we go. Let's change this to something like that, and something like that, and this to something like that, and something like that. It looks like that didn't work either. I think our lifetime for the line is too short. Maybe we should change it to something a little bigger. Nothing. Maybe if we change it to time.delta time. Nothing. Oh wait, it's up there. Whoops. It's kind of flashing though. Yeah, I have a guess for why it's doing that. So what we're trying to do here is make it so that when we draw a line, every time an update, it only lasts for one frame, so that when we make changes to that line in real time, it will look like it's updating the line in real time. But I think the reason it's not working is because the way our visualizer works, it has to send data to the GPU for each one of our lines. So on update, it will sync the data to the GPU, and then on this onRenderObject function, it will send the calculated GPU data to our vertex shader in order to be rendered, and it will also remove lines. I think what's going on is that when this drawLine coroutine gets called, sometimes this function will get called before update, and so it'll get removed before it even has a chance to render, whereas sometimes update will sync it to the GPU and then it'll render for one frame and then get removed. I'm actually wondering if we just take this part of the function and remove the lines in update instead of in onRenderObject. Maybe that'll be better. So that's kind of working, but our one line here still is kind of flickering like an incandescent light bulb that's dying out. Yeah, okay, I'm gonna change it back. Wait, what? I just went to put the code back. I didn't even change anything, and now it's working? Huh? Okay. I'm not sure what I did. Maybe that just happens sometimes and other times it bugs out. I'm not sure. But anyways, now we should be able to, with our handy dandy inspector tab, there we go, move this around like that, and it kind of looks like it's updating in real time. Yeah, there we go. Yeah, perfect. Let's see if we press play again if it's still flickering. No, it's still good. How weird. But why does that happen? You would think that when you put things back the same way, it would work the same way. I'm not sure what changed. Yeah, I don't know, man. I don't know. Just don't ask me. Don't ask me. I'm done. Anyways, now that we have that working, let's go back and see if we can implement this guy over here, the linear Bezier curve formula here. So we'll make this new function. We'll give it 2 vector 3's. There we go. We got the 2 points. And actually, let's just change this to linear Bezier. We'll take our 2 points and we'll also take a float t for time between 0 and 1. And we'll also return a vector 3. So I think that's our formula there. So we'll go up and change the names of these to P0 and P1, and then we'll start a loop down here in update. We'll set a resolution of 10. Okay, so now we've got a loop here that has a resolution. The resolution is basically just to break up the Bezier curve into little segments, little increments, and then we loop over each of those increments to draw different segments along the Bezier curve. So this should just give us a regular straight line. Yep, so it looks like it still just gives us a nice straight line. Wait, I forgot to save it. Never mind. Hold your horses. Oh yeah, something bugged out. Didn't give us anything. Oh, whoops. I know what it is. Yeah, because I renamed these variables, these reset to 0. Whoops. Let's try again. So now if I do this, oh, there you go. You can see it drawing at the bottom. And up, and up. There we go. Yeah, so it does still give us a straight line, which is good. That's a good sign. Okay, but that's kind of boring. I'm bored with that now. The real fun stuff comes when we get to the 3 points or more, the quadratic Bezier curves. So now we'll go ahead and implement this function here, to get curves looking more like this. So now what we'll do is duplicate this vector. We'll name this one P2, create a new function for quadratic Beziers. Hey, look, it's already kind of predicting what I want to do here. See, as I start writing out the equation for the quadratic Bezier curve, it's already predicting that I want to do plus t times P1, but it doesn't just stop there. Okay, so that should be the equation for the quadratic Bezier. Now I'll make another function to visualize that. And that's pretty much the same as what we did for visualizing the linear Bezier, except we just changed this to the quadratic Bezier function and add our p2 variable that we put up here. And then we just go up here and replace this. Visualize quadratic Bezier. Perfect. Oh yeah, look at that. You can see it. By the way, check this out. I can like zoom live by doing this with the scale. This is something you would usually do when editing the video, but I can do it like right here. Actually, you know what? I should make a function for my flying camera scripts to zoom in when I want to. That'd be fun. But yeah, check that out. It's made some sort of curve. Okay, so now I should be able to modify P2 a little more. So if we, okay, oh wait, I actually forgot that. Oh, P1 is our midpoint. Yeah, P2 is the end point. Okay, so then we can lift P1 up. There we go. Oh yeah. Wait, that's kind of changing our other endpoint though, isn't it? Am I missing something? I think I'm missing something. That because you see how that endpoint is moving up and down. The beginning is staying fixed, but the endpoint is moving up and down. I think I did something wrong. I don't think that should be moving like it is. But we're doing something right. I don't know why, but I can't help thinking that doing this reminds me of Crab Rave. I don't know, it looks like a little crab dancing. I can't explain it. Oh, you know what? I know what it is. I messed up my my loop here. This actually needs to be t plus increment. There we go. I need to fix that down here too, because otherwise that won't actually include the last point in the calculations, so we won't see it. So the last point in the curve that looks like it's moving is actually the second to last point. So now if we move P2 over here and move P1, there we go. See that? Oh yeah. Look at that. Now it's like a bowstring. Wow 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 wow. Brings me back to physics class when you're talking about standing waves. Yeah. Okay, that's pretty cool though. We got that working. So now we can define quadratic Bezier curves. But you can see the linear Bezier curve equation is pretty darn simple. Whereas when you go to quadratic Beziers, it already gets a lot more complex with more terms. So as you go to higher and higher order Beziers, I guess the number of terms that you add just becomes a lot. It just grows really quickly. That's why I want to try to do the general formula for this. But I also want to be able to see the points where P0, P1, and P2 are. So let's draw a couple of wire spheres where each of the points are. And then hopefully, I don't know if I have to do this in the onDrawGizmos function. I'm just gonna try it here. It's whatever. Yep, immediately an error down there if you can see that. Right there. Yep, gizmo drawing functions can only be used in onDrawGizmos and onDrawGizmos selected. Yeah, whatever. Okay, Dad. You see, this is why I have my own visualizer library that I'm trying to build. The gizmos is just so restricting sometimes, you know? So what I'm gonna do is I'm gonna build another function for drawing n-gons. So I'll be back when that's done. Okay, so I have stolen some code now from my draw cylinder coroutine function in order to make this draw n-gon coroutine function where we can specify the position, sides, radius of some n-gon and just draw it. So now in my test script, I've replaced those gizmos lines with that. So that now when we run the script, we get these little green squares that can show us where the actual points are. Boom, check that out. So there's point 1 right there, and point 2 there, and then point 3 down there. So then when we take these points and we move them around, you can see exactly where the points are moving to and how it changes the nature of the Bezier curve. Also, I'm kind of sick of having my camera move around while I'm trying to change variables, so I'm gonna fix that real quick. My flying camera script. So I put this flag boolean here to tell camera whether it should move, and then when we press R, it should park itself down so it stops moving. Okay, perfect. Now I press R and move my cursor around freely, and now we can play around with these points however we want. Perfect. Okay, I think the next step is to generalize this and start doing the general function for higher order Bezier curves. So let's go ahead and do that. Okay, now what I want to do is do that thing where we can zoom in with the camera whenever we want. So I think I'm going to change the field of view for the camera in code so that when we zoom in, it goes like this. Zooms in on something. We'll use F for focus. So I think this should change it. We just get the camera's component, change its field of view to 30 when F is being held down, and then 60 when it's not. Oh yeah, there we go. Check that out. That's actually kind of fun. You can just zoom in on stuff just like that. Very nice. It's 30. Now it's 60. Now it's 30. Now it's 60. It's 60. It's 60. 60. It's 60. Okay, let's implement the general Bezier curve now. So we pull up the Wikipedia page again. Okay, so we've been doing the quadratic Beziers. We're gonna skip cubic and just go straight to general definition. definition. So the sum we can probably just implement with the for loop, and then for this binomial coefficient, we'll replace that with this guy down here using factorials. I don't even remember how to do factorials in C#. Like what function did it call for that? I don't remember the name. We're gonna have to figure that out. And then just a couple exponents here, yada yada yada. Okay, whatever. Looks easy enough. Okay, now this should be all the code that I need to get this to work. Can you believe this is everything we need for Bezier curves? So we do a for loop to put all the different terms in the polynomial into this sum vector. So this is the binomial coefficient, that one part of the equation, this part right here. So I made this little factorial function because I guess Unity doesn't have its own factorial function in the mathf library. So I just use a ternary operator to do that. And then we add a new vector to the sum and then return it. And then we have this other visualize Bezier function that's slightly different from the other ones. And we'll just have a list of points that we can use, and we can increase the points and decrease the points and do whatever we want to make any sort of Bezier curve we want. Hopefully. Maybe it'll just break. I don't know. Hopefully get some nice curvy lines out of this. Okay, we park here. So we've got two elements, and let's bring this one up. Bring it up. There you go. Move you over. Bring you up and over. So there's our linear one. Now let's try adding a third one. Oh, that's weird. That doesn't look good. Uh-oh. We've made a lambda function, or a lambda symbol. I don't know what they use for the wavelengths, you know, in physics class. The lambda symbol. Okay, we clearly didn't do something right though. Ooh, this might be the problem. So I just did a bunch of tests to just make sure my factorial function was working, and I just got a bunch of ones out. So I think I did something wrong there. The rest of the code might be right. Oh, whoops, I know what I'm doing. I'm not actually doing the factorial part, duh. I need to actually multiply x by the recursive factorial function. That should be good. It's the simple things that get you in programming. There we go. Now we're getting some better numbers down here. Now let's actually try to run our visualization script again. Okay, so bring up this one, set it over here, bring up this one, set it over here, look good. Okay, moment of truth at a third point. Okay, well, it's not looking the same as before, but it's still obviously wrong. So it looks like the line has jumped from our 0th and first points to the 0th and second point, our new one, and then completely ignored our third point here. Oh, I know what it is. I know what it is. I've been made a fool again by integer casting. That's what it is. This needs to be a float. I bet my life on it. Do you know how many times I've fallen victim to that? Too many. Okay, let's try another time. Here. Okay, moment of truth number 2. And boom. Nothing. Okay, well, I guess I'm dead because I bet my life on it. I tend to do that a lot, you know. I'd be dead years and years ago if I actually got punished for the things that I bet my life on. Wait a minute. Maybe I'm still being taken advantage of by it because there's 2 integers. Because this factorial function returns integers, so we're still doing integer division here, and then it's being turned into a float. Let me do some debugging just to make sure. Yeah, so it looks like when I log binomial coefficient, it's coming out as either a 1 or a 2. So yeah, that's probably definitely not what we want. So if I cast this to a float, perhaps that will fix it. Nope, we're still getting a bunch of 1s and 2s. Oh my goodness, I just realized what it is. Okay, now I bet my life on it. All right, listen. So these numbers down here, the Bezier curve was always returning the value of the endpoint, and that's why it was jumping straight to the endpoint and ignoring all the other points. Okay, what did I say about the little things always getting you in programming? Yeah, here, look, I'm multiplying in the polynomial by the nth vector in our list instead of the ith. When we're looping over to sum from 0 to n, I'm just putting in the end vector all the time, so that's screwing things up. So now if we just change that to I, there we go. Goodness. You know, sometimes you have the concept right, but there's just the tiny little thread that's holding you up, and you have to figure out what it is. Okay, I gotta delete all these debug logs though, they're gonna get in my way. Okay, now, let's do this again. Okay, moment of truth number 3. Numero 3. And, there we go. Yeah, I think that's working. Just move this one over again. Oh yeah, it's doing its thing. Okay, let's do another one. So, this one has 3 lists, so it's technically a 2nd degree Bezier curve. So now this one will be that's a quadratic. This one will be a cubic 3rd degree Bezier curve. And now we move that. Oh yeah, there we go, baby. Oh yeah, look at that. Now we can take this down and kind of squash and stretch in really whatever direction we want to now. So let's take this over here. And maybe I also put this parameter for the resolution. If our resolution is at 0, it's just a straight line. Whereas if we... Oh, why is it stuck? Uh-oh. I froze it. I froze the program. You know why? Because when I set the resolution to 0 in my code, yeah, it's dividing by 0 here now. So I think that froze it. Whoops. Task manager, save me. Don't let him kill me. Okay, Okay, it's dead. Let's do it again. We have to modify this so that that doesn't happen again. So we'll just say if it's 0, whoops, get it out of my way. I'm trying to explain something here. So if Bezier resolution equals 0, then we'll just set it to 1. So now we can set up our points again here, but you can see it looks kind of blocky. So now what I should be able to do, now when I turn down the resolution again, there we go. You can see it just stays at 1. I can't turn it down any further. Wait, uh-oh. I didn't freeze it again, did I? I think I froze it again. Does this not work? Maybe I should just do this a simpler way. Go mathf.max between the Bezier line resolution and 1. Okay, so when we turn up the resolution, you can see those line segments getting smoother and smoother. And when we turn it down, they get blockier and blockier, so we can extract less detail out of the line. And now hopefully when we turn it all the way... Wait, what is that? Why is it going past the point? Okay, that's weird. Now that shouldn't be happening. Whatever. It's only happening at 12, I guess. And when we turn it all the way down... Yep, looks like that's working. There we go. Yeah, I don't know why sometimes it goes past the line. Yeah, that's strange. That's inhuman. Okay, yep, so when we go all the way down, then it's just a straight line, and the higher we take the resolution, the more detail we get out of it. Perfect! Perfect, perfect. Let's make something even more complex. So we'll put in another point. Maybe we can make a kind of M, bring this down, slide it over here, bring this guy up, bring this middle guy way down, and this guy up, this guy up. Yeah, I don't know if I would call that an M, but you know, you get the idea. So using this, we can make lots of different kinds of shapes for our leaves. Hopefully. I think this would be good enough. But of course, it does tend to be kind of smoothed out. So I'm wondering if we can only make smoothed out shaped leaves, or if it's actually possible to get jagged points using this. I don't know if we can do that without sort of stringing together multiple Bezier curves. Yeah, I'm not sure on that one. So we'll have to do a bit of experimentation and see what we want to go with for the final model. Okay, so how are we going to take these Bezier curves and turn them into actual leaves? So it's very simple. Let me show you right now. So what we're going to do first is take our leaf shape and divide it up into a bunch of vectors so that we can take those vectors and spline them together into a large high-dimensional tensor. And then we'll take that tensor and feed it into a neural network that can process it from a high-dimensional space into a less complex Einsteinian relativistic surface so that we can then computationally simulate two entangled particles from each side of the surface and then create a simulated wormhole to teleport these particles through to the other side. And then we can take that data and feed it back into the definition for Darwin's theory of evolution, which states that... Andy, are you still with me? Hang on, let me turn on my camera. I'm just kidding. What I just said was nonsense. That's not actually how we're going to do it. It's very simple. Very simple, Andy, so pay attention. All we do is take our Bezier curve. We have one arrow, one vector from the start point to the end point. We take one more orthogonal vector at 90 degrees to that one, where we place the first Bezier curve, and then another one going the opposite direction, where we reflect it and put the same Bezier curve in the opposite direction. And that's it. We have a leaf. So we just need to take out our draw ground function, and here, whenever we draw a line for the Bezier curve, we will also draw another line, except this new line has the same information, just with the y values flipped. So now what we can do when we draw our line is reflect it like that. Now right now we're doing a hard reflection just along the y-axis, but when we do this on the actual trees, we will have to calculate the vectors according to the direction that the leaf is actually supposed to be facing, rather than always just being stuck on this x equals 0 line. And once we do that step, we should be able to generate these leaves with the Bezier curves alone. So we can make narrow leaves like this, ones that look like an airplane wing, or we can make them wider. We could even do something funky like this and make like a twisted infinity leaf, or like a fish that's swimming, or ooh, something like, oh no, what have I done? Uh-oh, you didn't see that, kids. Let's see, I'm trying to make like a heart shape. That's kind of a heart-shaped leaf, yeah. Valentine's Day is coming up. You have a Valentine? I don't. See, this is kind of like an arrow. So essentially, using this system, we can make open leaves if we mess with it like this, but that kind of actually breaks the closed leaf shape. In order to not break the leaf, we need to keep the end points on the 0 line of wherever we're drawing our symmetry, and then we can just mess with the middle points in order to get whatever type of closed leaf shape that we want. Oh, this one looks kind of cool. It's like a star. There we go. We just made a star leaf, and you can almost make it look like it's rotating by moving this around a little bit. So anyways, looks like there's lots of cool things that we can do with this. So now what we need to do is go ahead and implement it into the tree class. and get some actual leaves on our trees. So now I just finished writing this script for draw leaf, where we take 3 orthogonal vectors together and use them to draw both the top half and bottom half of the leaf, and then we visualize them at the same time with 2 different Bezier curves. So now it should happen when we move some of these points out. Let's get the direction going this way. Okay, let's move this over and this over, and then bring it up like this. There we go. And one like this. Okay. And now we should be able to change this base position of the leaf. There we go. It's moving. And then the Y position. Okay. If we just move around here to get a little bit of a better view of what's going on. So you can see right now the leaf is laying kind of flat on the ground. So now let's park here again, and we'll change the position, move it over here, and we'll change the direction. We can tilt it up like this and around, and then we should be able to flip its direction going the other way. There we go. So you can kind of have it flap in the wind like this. That'd be kind of cool to add a bit of wind that we use to simulate the positions and they change dynamically. Yeah, that'd be nice. And then if we change the Z, looks like it's tilting one way or the other way. Okay, all right. Looks like that's working. I didn't even have to rewrite anything. Very, very nice. Okay, well, this is essentially the foundation, which we will use in order to draw these leaves on all of our tree branches when they terminate. Let's make kind of an infinity leaf and go like this. There we go. And then just kind of spin it around. Looking very nice. Let's turn up the resolution again a little bit. Go. And move it and spin it around a little more. Looking very good. Well, okay, I think it's ready to go on our trees then. So what I'm essentially thinking in our tree class here, I'm going to add a couple more funcs here. One for leaf divergence when they grow at the end of a branch, and another one for how many leaves should spawn at the end of a branch when it terminates. And then down here in the constructors, we'll add another spot for those functions, and one more for a list of vectors describing the leaf points. So that'll essentially tell the tree how to build a leaf every time it does. So I'll go ahead and add those in, and then we should be getting some leaves spawning at the end of every branch once it stops growing. Okay, so now I've put in a few things. First of all, a leaf base position for the point where the leaves spawn on the current branch, as well as a list of leaf directions where each leaf on the current branch is pointing to, and a list of points for each leaf's Bezier to act as the blueprint for how the leaf should be drawn every time we spawn one. Then also in our grow function, if we're done growing, we will spawn some leaves, and what that will do is set the leaf base position, get the number of leaves to spawn, and then add a bunch of leaf directions to that array based on our last segment from the current branch. So now all we need to do is go back into our test script and add our drawing leaf function to our pre-existing tree drawing functions. Okay, so now I've made a few changes to the test script. First of all, I've changed the visualize Bezier to an IEnumerator function instead of just a void function, and that way we can choose if we want to have the Bezier curve kind of draw out in real time or just draw instantly. So if should wait is true, then it'll wait a little bit for 1 frame before drawing the next line in the leaf, so that way it looks kind of nice and presentable when we're drawing the tree. And then for our draw branch function, every time we draw a branch, all of these cylinders in the branch draw first, and then at the very end, it will draw all the leaves. So for each leaf that we have at the end of that current branch, it will call draw leaf, which will then calculate all the points for the leaf as before with the correct rotation and everything, and then call the visualize Bezier with true for that middle parameter so that it looks all fancy. Although I should probably add something here so that after we draw a leaf, we also wait for a frame. That should look nice. Let's go test it out. So now we should just get a default tree when we play here. Oh, error already. Let's see. Tree 264. Oh, I know. We didn't actually initialize our list here, did we? Yes. There we go. That should be good. And, well, we don't have any errors, but no trees are spawning either. Oh, duh. I actually make this mistake quite a few times. First of all, I need to take this and only do it when we press T. T for trees. And then since visualize tree is actually a coroutine now, then we need to treat it as such and call start coroutine. Oh, and we can probably turn our ground back on. Okay, now when we press T, it was a little slow there. Okay, well, we got our tree. We don't have our leaves. Let's see. Argument out of range exception from test 41. Oh, actually, I think I made a mistake down here when drawing leaves instead of leaf points. No, we don't actually want this. We want to directly put in branch dot leaf Bezier points. There we go. Okay, let's try that again. Press T. Oh, what? Did you see that? Hang on, let's try that again. This time, let's give the tree a lifetime of 5 seconds. and T. Okay, it looks like it looks like our branches were sparking. That was funny. Let's try that again, and yeah, that looks like a firecracker. Okay, interesting. I almost kind of like it that way. It looks kind of cool. There's just spark in there like a little firework. Okay, well the lines for those aren't lasting, so let's see what's going on here. Oh, of course, because we set our lifetime for our draw line to just this very small number because we used to be calling it an update so that we could change it every frame. So let's just set this to 5 for now also. Okay, and T. Oh, yeah, it looks like it worked. And again, okay, let's pause right there. So you can go into editor mode and kind of, yeah, it looks like it kind of worked. The leaves are a little bit big, but yeah, otherwise that totally worked. So you can see at the end of this branch here, you know, once this cylinder gets to the end, it terminates right here and then it spawns a bunch of leaves. Perfect. Yeah, we just need to make those a little bit smaller. And holy cow, my Mexican neighbors are blasting their music so loud I can barely hear myself speak. Calm down. Goodness gracious, it's not the Cinco de Mayo. Okay, let's go down here and make these leaves a bit smaller in our default function. So we'll multiply this by 0.2 so that we're kind of dividing it by 5. So then that would make this 0.04 and this 0.06, correct? I believe so. By the way, if you're Mexican and you're watching this, no offense, you know, I like quesadillas and my family has a lot of Mexican friends, so you know, we're chill, okay? I think these leaves are a little bit, are they too small? I can't even really tell. I think we just, honestly, I think there's just not enough of them. Like there's not enough, there's really not enough branches to have leaves on them. I think these are a little small still though. Let's make them a tiny bit bigger. Let's see. Yeah, that looks okay. Yeah, let's see. Yeah, that's looking alright, honestly, but they do kind of look like, I don't know, daggers. Maybe we should add a little bit of action in the Z direction, because I actually just kept that at 0 here. I never actually changed this to something like, or actually, we should copy this one and then put that here and then give it a little bit of Z tilt like that. So that way it should make the leaf curl in a little bit towards the end, I think. I'm not 100% sure. Let's see if that's right. And it looks like, can't really tell. Yeah, I'm not sure. Do you see any curvature in that? Because I don't know. Maybe we should try a little bit more. And spawn? Maybe a little bit. Kind of see that towards the base? Is that it? I think I should do some more experimenting with that, but otherwise, the tree is looking kind of good. It actually has some leaves now. Yeah, very nice. Very, very nice. So let's try and draw our leaf again instead of a tree. So we will get some points here and set this way and that way, like this. Oh, that is what is going on. What? And when I move, okay, it's because of that weight function that I put in. So it looks like I actually kind of like that. That looks kind of cool. It's like a kind of breathing. Interesting. Okay, anyways, so what should happen when we tweak the other parameter here on this Z? Okay, yeah, there we go. So it is curling. And what if we tweak this Z parameter a bit? Okay, all right, and we'll put this. Yeah, so you can get a leaf curling like this. Yeah, so if we plug in our parameters here that we had for the tree, this is the type of leaf that we were generating there. So if we want this to curl a bit more, I guess we do something like this, or we could turn it into the Nike symbol. Yeah, something like that seems fine. Okay, so Z.25 on this one here. Okay, so now when we draw a tree, we should get them curling a little bit. Yeah, there we go. Okay, so yeah, right there. Yep, you can see all those leaves kind of bending. Very good. Very, very good. Okay then. Well, what I want to do next is, just like at the beginning when we were testing out with the Bezier curves and we were able to tweak the settings here in the inspector in real time, I want to set up these trees so that we can tweak the functions for how the trees are generated and the leaves are generated in real time. So that instead of being like this, where I just have to press T to generate a new tree every time, and then after 5 seconds it'll just disappear like that, I want to actually be able to keep the tree here and be able to tweak it in real time and see the changes to the tree in real time. Okay, so this was actually pretty unexpected. The first time I took out the press T condition and just put the tree so that it generates a new one every second that only lasts for 1 frame, and I didn't realize exactly what it would do when I would try it, but check this out. It's a tree geyser. It's literally spewing out 1,000,000 trees per second, and that's because every time it generates a new tree, it generates it with a little bit of randomness. So that randomness is different every frame, and since I didn't change the randomness randomness function to work with a seed so that it's the same every time, it just keeps going like this. So every frame, it is generating a new tree that only lasts for like a frame, but it's also generating a different one each second. So we just get this continual stream of random trees of the same type just gushing out of the ground, which I think looks pretty insane. It's actually kind of cool. We can go into orbit mode to look at it. Yeah, that's pretty much a firework all on its own. Anyways, enough messing around. Okay, so what I've done now is I have taken and serialized a bunch of animation curves, and these will serve as places in the inspector where we can customize our functions. And then I've taken all of our funcs from our tree class and copied them over to the test script so that whenever we call them, they refer to the animation curves and use them to determine what the tree looks like. And then in order to get not a truly random tree each time, but the same kind of tree each time, we initialize the state of the random generator every frame so it produces the same random values. So let's see what that does. And I think we better pull this down so that we can see all of our functions here. Actually, you know what? We better make the functions first here in the editor before actually going into the tree, because otherwise we could get some bad things happening with recursive functions and then it freezes our entire program. Okay, so I've set up some baseline defaults for these functions. Most of them I've just kept at the default value of 1 up to 100 so that they can cover up to a segment number that gets to 100. I don't think they typically get to that point, but I don't know, it should be fine. So now, if everything's working correctly, we should see a very weird tree popping up now. Oh, yep, there we go. There it is. It's kind of spiky looking up there. Can you see that? Sure, we don't want to sit on it. Oh, nice. Yeah, that's kind of funny looking. Interesting. All right, that's not the point. The point is now we should be able to, let's mark here, and now if we go select our test script, we should be able to change these functions and see the results live. So let's see if we change this branch divergence. If we, for example, take this and go up with it, no changes. Or maybe it is changing and we just didn't change it enough. Oh yeah, I forgot, the scale of this is totally bonkers. Let's zoom out here a bit. Let's take this way up. We turn it up. Oh, do you see that? You can see the branches moving kind of. Oh yeah, look at that. It's swaying. If we take this, let's just edit the key. We'll make the times 0 again and make this value 45. Boom. Oh yeah, there we go. Okay, we need to change the scale of this. Okay, perfect. There we go. Now you kind of see the values it's dealing with here. Let's see if we, oh. Yeah, that looks kind of weird. Tilt that down. Kind of play around with this a little bit. Kind of looks like a bunch of staples as it, I don't know, man. That was really satisfying. Just, a little too fast. Okay, interesting. So we'll tone that down. I guess that's fine. Now for branch rotation, I do always want this to be dealing with 360 so that it always has the opportunity to rotate 360 degrees around the trunk. And now it's a little bit tall and out of view, so let's take it down a notch. We'll take the segment radius curve, change it to start at 1. Ooh, okay, that's lagging a little bit. And we'll change this down to -10. Oh, nope. Let's go back up to -5. Okay, maybe a little bit more. -3. Okay. And these we can also kind of tone down like that. Or, that's not good. You gotta be pretty careful with these measurements, because just a little bit of a fine tune can kind of send it crazy. Yeah, send it crazy. I don't know. So you can kind of see how by tuning these parameters, it kind of stays at the same tree, but it also evolves a little bit due to the pseudo-random numbers that we're using. So for example, that first branch that branches off at the bottom stays there, but other ones can be added or not as we change it. I don't know, it's kind of weird to wrap one's head around. Okay, I think right there is about fine. And we can change the divergence of the segments. Let's put this at somewhere like 10. There we go. He's looking a little sad though. It almost looks kind of like a coral plant. Oh, you know what though? I just realized something. The reason it's actually bending all the way in the same direction like this, like every one of the branches is curling in the same direction. The reason that is also because of the pseudo-random numbers. So once the pseudo-random number picks a direction for the branches to turn in, they all turn in that direction. And I don't think that there's really a way around that without just putting in some more additions that are going to be a little bit annoying. I don't know. We could do pseudo-random numbers for each one of the different functions themselves, but I don't know. That's just going to be annoying. You know, dealing with these functions is already kind of annoying annoying. It's a little bit hard to play with. So I think I'm probably just going to go back to the old-fashioned generating them from scratch every time. Plus, there's really only so much that you can do with these functions. You can get a lot more diversity when you just code functions directly and explicitly without having to deal with these curves and stuff, but it is kind of nice seeing the changes in real time. That is fun. Anyways, I think I'll take this back down to 5. Whoa, let's see if I tilt this a lot, like, oh, let's see, where was it? It was like, oh yeah, like that. Whoa, what's going on? And whoa, wait a minute, how did I do it? I don't remember how I did it, but anyways, you could kind of use this to, you know, if we change the random numbers ever so slightly, you could kind of use it to make it look like the tree is swaying in the wind. That'll look really nice. Yeah, I think I want to try that. So we could bring this up to 360 as well. Perfect. And then we can also change how many branches are spawning here by changing this guy a little bit. So the higher we put this, the more likely a branch is to spawn. We can take this up here like so. That's not really changing too much. So if we take this segment divergence angle function and we just bring it up a little bit like this, and you can see the trees will kind of get a little more crooked as we bring that up. That looks pretty nice. And we just keep going up with that and going. Come on, I want my tree to be a little twisted here. There we go. Oh, that is satisfying. Whoa, that's kind of interesting. What is, the way this works, sometimes some weird things kind of shift. It's almost as if, like, have you ever seen those kind of fourth dimensional simulations where you kind of change time and you're seeing the same 3D object, but you can also sort of move through the changes that happens as time goes on? So you can see, like, right here, it sort of passes a threshold where that bottom branch flips over and starts kind of growing up from the ground. So now we can change these leaves. Let's change how many spawn. So we'll edit this to be, let's say, 10. Okay, and this one will also be 10. And now we need to separate them by changing the leaf divergence angle, which we can do by changing this. And we'll bring this to, let's say, I don't know, 100. There we go. You can see those leaves just separated there. And we'll bring this to 100 as well. There we go. Now let's rotate it a little bit. We can put this at 360 degrees as well. There we go. And same thing right here. And okay. And now we can kind of change the shape of leaves by moving these around. We can make them longer, kind of like that. Okay, we can bring this up. Oh, beautiful. Okay, we can curl them around a little bit. Let's see. We change this a little bit. Oh, there we go. That's curling them a tiny bit. Let's make them a little smaller. Okay, I think we went a bit overboard here, but it looks very nice. Okay, let's tone this down a bit. Bring this like that, and this like that. There we go. That looks a little bit tropical, maybe a little bit swampish. Yeah. And oh, this one's negative. We need to bring that back up. Let's make that positive. It just kind of, oh yeah, that just kind of flows, doesn't it? That just kind of flows. Beautiful. Okay, let's bring these in a tiny bit again. It does look a little bit choppy though when I'm changing it. I think if we take the resolution up a little bit, that might kind of fix it a bit. So then when we make those changes, it still kind of looks a little bit pixelated. You can just see the smaller lines as it changes. But you know, other than that, I think it's looking pretty nice. So you can bring this back. Yeah, I don't know. Anyways, I think I'm going to be switching back to the other method now, where I just kind of come up with the functions previously and then we'll just run them independently. Instead of, you know, using these functions, I'll just program the tree functions explicitly to get exactly what I want. So I think what I'm going to do now is go back to all of these trees that I made in part 1 of this tree generator series, little mini series. I commented them all out here, but we have our tree of life, snake tree, spiral tree, tentacle tree, mangrove tree, kapok tree, acacia, joshua, baobab, sugar maple, pine, and angel oak. I think I'm missing one. Nope, I think that's it. Now I'll go through and just kind of try to create all the different kinds of leaves that are present on these trees, so that instead of just having the branch structure, we can actually, you know, it'll actually look more like the tree. Because in the previous video, when I did the showcase of all these trees at the end, they were really just skeletons. They didn't look too much like the actual trees due to the lack of actual foliage on them. So now I'll be trying to replicate that foliage and come up with a few new trees besides these ones, and we'll see how that goes. I'll be back in a little bit. Okay, so I've been doing some more coding, some more testing for the last little while, and I collected a bunch of interesting bugs. Come see my bug collection. The first bug is this weird thing that happens with branches when they rotate, which I still need to fix. Basically, when the branches bend a certain direction, there will come a certain point where it just flips up like this due to the cross product that I'm using, changing directions at a certain point. So that still needs to be fixed. I also put in a parameter for changing the leaf color. I thought that'd be nice to make a distinction from the actual branches. Wait, hang on. Did I just make the Indian flag? Let me look it up. Oh my goodness, I pretty much did. Hello everybody and welcome to another coding tutorial. Today we are going to be making an infinite tree generator. I don't know. I can usually do a better Indian accent, I promise. Yeah, if you're from India, don't worry, we're chill. I don't know. Was that too much? Was that too much? Maybe that was too much. Oh boy. Anyways, I also found out that when I set the custom colors for the leaves, it turns out really glowy. Yeah, like you can go right up close to it and see it's just, yeah, it's too much. So what I had to do is change this here by setting this to dot gamma, I guess, apply a gamma curve to the HSV color, I guess. And that makes it less glowy, I guess, but it's still kind of too much. The only good result really that I've gotten from this is just to set this to the color that we have in the inspector here, so that way the leaves look like this and they're a little bit more toned down, but still kind of glowy a little bit. So there you go. Behold, the maple tree. So I mean, look, maple leaves are pretty complex. I mean, I had to take, something like this. Can you imagine how many Bezier curves, how many points it would take in order to represent all of these different jagged edges? So I just kind of approximated the large points so that it takes the form of this kind of star-ish shape thing. I don't know, I think it looks fine. So there is that, the sugar maple tree, and I also added this random seed parameter so that we can change the number that is used to generate our random numbers. So we can change this in real time and get a different sugar maple tree with every seed. Okay, I'm done. Oh, by the way, that issue with this bending tree here where it bends upwards after a certain point, the AI has decreed that apparently we're having issues related to the hairy ball theorem. Yeah, I'm not gonna ask what that is either, but I think I still have an idea for how to fix that. Okay, so in order to fix that issue, what I've done is I've had to create a new variable in our tree class that stores the orthogonal vector, and then when we actually diverge the vectors to create new segments and branches, we kind of rotate the orthogonal vector with the vector that we're diverging so that they sort of stay together and are a little bit more aligned as new segments are created. So hopefully that fixes that issue. So let's see if we try bending this again, and okay, that's working. And the other way, okay. And now if we rotate this 90 degrees and try again. Yeah, what are you doing, bro? What is happening? That is just the weirdest twist that I've ever seen. Okay, yeah, that's odd. I mean, at least it's kind of keeping continuity and it's not really flipping so dramatically like it was before, but this is still kind of weird behavior. Yep, I think we're going to have to visualize where the actual orthogonal vector is going when we call this diverge function down here. Oh, you know what? I know what's happening. The reason it twists weird like this when I rotate it is because back here, no, here, up here, in my function for getting the segment divergence angle, I just set it as a fixed number. So it's actually rotating that much on both of these segments instead of just the base one down here because of the way we changed how the orthogonal vector rotates. So I think this piece of logic should fix that. I feel like I say that too many times. Yep, this should fix it, and then it doesn't. So now if we bend it a bit and then rotate it around. Yeah, that seems to have fixed it. Haha, it did work, suckers. So now if we turn this around here, there we go. That's more expected. Okay, well that should be good enough. So now, okay, this is the actual thing that I'm trying to get to with that. We can take out this test tree, draw our sugar maple again, and then down here you can see in the function for the segment divergence angle, I've added in our branch bend factor, and this is what that does. So we can set up camp here, pick a random maple tree that we like, that one's fine, and then when we increase or decrease this branch bend parameter, you can see it kind of makes it sway a little bit. Yeah? So what it used to do is when you would change it a little bit, because of that flipping that was occurring at certain angles when the segments bent too far, it was kind of looking unnatural when it was swaying like this because some of the branches and the angles that they were at would cause them to flip into different positions, so it looked like they were teleporting around the tree. It was kind of weird. But now we can change the bend as much as I want. We can shrink the tree down into this little ball heap of mass. It looks like a yarn ball or a cell, a fetus, an axolotl, I don't know. And then we can kind of unwind it again and watch it spring up and turn into a maple tree. But what I want to do is set up something that can automatically change this bend parameter by a little bit over different frames and just kind of lerp it back and forth like this so that it looks like it's just, you know, swaying in the wind. Although we also need to add a little bit of rustle to the leaves as well. So if we add our branch bend parameter to our leaf divergence function as well, let's see what that does. Okay, yeah, that's, it looks like it's maybe affecting them a little bit, but not too much. Yeah, I want to give the leaves a little bit more rustle than the branches. The branches shouldn't move a ton, but the leaves should be blowing around a little bit. Okay, so let me show you all what I've done so far for this. So first I had this little bit of code here in order to try to get the tree to sway a little bit by moving the branch bend by a random number each frame. And that went kind of hard. It looked like it was giving the tree some seizures. Yeah, you can see it's kind of jittering there a little bit. It looks very unnatural. The bro needs to take his meds. So then I replaced it with this bit, which uses a branch bend multiplier in order to change the direction of where the branch is bending based on a certain chance every frame. And that looks a little smoother, but it's still a bit unnatural. Like you can see, it is kind of swaying there, but then when it changes direction, it does so kind of abruptly. Like you can see those when the branch is swinging, and then it'll kind of like stop for a minute and then go back. So it's looking a little bit more natural, but still not too great. So I think I can do a little better than that. By the way, I was still having issues with the colors of the leaves appearing too glowy before when I used this maple leaf color. I found out it was because I was using values greater than 1 here. I need to convert it to fractions of 1. And also the dot gamma here wasn't even necessary, so that's good to know. Okay, so I added more variables for branch bend. I added branch bend acceleration, velocity, regular branch bend, and then branch bend sigmoid. And basically what that does is it traps the amount that our branch can bend inside of a sigmoid function here so that it can only go between 0 and 1. Wait a minute, maybe we should do a hyperbolic tangent function instead, because I actually want -1 and 1, not 0 and 1. Whoops. Anyways, I'll change that in a bit. Stop showing me pictures of sigmoid colon. Jeez. But the branch bend is like the X along that sigmoid graph, and then it has a velocity, and that velocity can be changed by an acceleration, and that's kind of supposed to slow things down so that we don't have immediate changes with the swaying, where it'll kind of sway to one side, and then if it wants to go back, it'll slow down and go the other way. So the changes in velocity are kind of softened. Yes, let's see. This is the one we want, the hyperbolic tangent function, to go between -1 and 1. And I know this because I've built my own neural networks before, and these are used for activation functions. Activation functions. The sigmoid and the hyperbolic tangent function. Yeah, here we go. Here's a good picture of that right there. Neural networks. Yeah, I've built a couple of them from scratch before, and I know that a lot of other YouTubers have done sort of their own AI projects, like AI learns how to race a car on a racetrack, or AI learns how to play the dinosaur game or whatever, you know. But if any of you are actually interested in me creating some of those projects as well, let me know in the comments, because I'm super into AI. I love to make neural networks. This is a pretty weird equation for it too. E to the x minus e to the negative x divided by e to the x plus e to the negative x. Okay, which means we need to change this into this. I believe that's correct. Yes, this is e to the x minus e to the negative x divided by e to the x plus e to the negative x. Yes, that should be what we want. Let's see, is that working? It's not moving a ton. Yeah, it's not moving a ton at all. I wonder what's going on there. It actually was moving a little bit before. Perhaps we need to clamp the x range of our branch bending. Yes, I've clamped the range in between -10 and 10, because as you go out further to -infinity and infinity on the hyperbolic tangent function and the sigmoid function, it gets very, very small. So maybe it was running off in one of those directions and you just couldn't see the change anymore. So let's see. Okay, it's moving. Now it's still just kind of frozen again. Oh, no, it's kind of jiggling. It's jiggling a little. Oh, it's shifting. It's shifting. Okay. I think we need to display these numbers again instead of keeping them private so that I can actually see what's going on. B and boom and boom and boom. Yeah, so it looks like the bending is kind of slower now, but it tends to want to hang out still at one extreme or the other. So I think it's just a matter of fine-tuning the parameters. So I think I'm gonna do that and come back when it's set at something that looks nice. You know what? Actually, I have a different idea. I wonder if we can set this up somehow so that it's kind of like a spring, because trees are kind of like springs springs, honestly, if you've never thought about it. You know, they have a certain shape and they can get blown in one direction, but then they tend to spring back and oscillate back and forth. That's what I think I'm missing here. So what I need to do is get some spring equations incorporated into this, and then have some forces push it around a little bit and have it just oscillate. Yeah, that should be nice. I think I'm just going to give that task to the AI to see if it can whip something up real quick. So we're going to use a new model that was recently released. Okay, it's thinking. Yeah, so it gave us some new variables, a spring constant, damping coefficient, and impulse magnitude, and then uses the spring constant to pull the branch bending back to 0, and then the damping coefficient to moderate the velocity of the branches a little bit, plus the random impulse to simulate the wind gusts. And also, apparently there is a tanh function in Unity. I had no idea. I should have known. Okay, well, we'll just take what we need from here. We'll plop our spring constants in there. Need to change this to tanh. We'll take this line for our wind, plop it there. Our acceleration, and then the last bits. I don't like copying all the comments that it places all over. Wait a minute. Why isn't tanh defined? Well, I guess we can just use the one from system. Okay, let's see if that does the trick. Looks like it's still not moving too much. Just a tiny bit, but it's also kind of doing that erratic seizure behavior that we were getting in the first place. Let's see what happens when we change these spring parameters over here. Let's increase the impulse magnitude. Let's go a bit more. Okay, actually that looks kind of interesting. Yeah, I think I like it, but of course that's a little bit too much for the branches. What we want to do is keep it subtle for the branches and more obvious for the leaves. Yeah, I think something like 3 is okay. It's a little bit subtle and not too erratic, and kind of gives the tree a little bit of life. Yeah, I like that. Okay, so I basically just duplicated all of the variables for the branch bending and made some new leaf bending variables, and did the same thing down here where we calculate the acceleration, velocity, and actual bend values. I also took out the tanh function. I just don't think it's necessary, since because we have the spring oscillating around 0, if the parameters are fine-tuned, it shouldn't really need to be limited in between -1 and 1. And then down here I am also adding the leaf bend parameter to our leaf divergence function. Okay, I'm actually not sure if this is working or not. It almost looks like, I don't know, the leaves are kind of out of control with this one. Yeah, they kind of just start flapping like butterflies, which isn't exactly what I was going for, but by the way, isn't the shape of this tree just so aesthetically pleasing? I like it, at least from that angle. Ooh, if you look at the backside though, oh yeah, they're really flapping now. I think I need to turn up the damping coefficient just a little bit, and maybe turn the spring constant down some as well. Yeah, I don't know. It's really not too lifelike the way it is right now, but whatever. You know, this is a synthetic tree. It's not a real life tree. It does its own kind of special dance with the wind, its own little randomly generated and yet orderly dance. So, yeah, you know, I'm okay with it. I am okay with it. I do kind of want to get rid of these shifting cylinders though. You can kind of see as it's moving, it leaves some of its previous self behind. Yeah, I do want to get rid of that. It's kind of a sore to look at, kind of a pain to look at, and I know exactly why it's happening, so I think I'm gonna go fix that right now. All I need to do in my visualizer script is go back down to my chunky cylinder drawing coroutine, scroll all the way down to the bottom, and put in this tiny little bit of logic. If draw duration is greater than 0, I think that'll fix it, because if it is 0, we don't want to wait at all, because if we do wait at all, we'll probably be waiting at least a frame for the next set of lines in the cylinder to draw, which isn't good enough when we're updating the tree every single frame. Let's see, do you see it? Yeah, it looks like it worked. I don't see any more of those residual lines anymore. Well, I guess we did it. We got a nice little gusty tree. Gusty, soothing little maple tree. Okay, well, I think it's time to, first of all, add a little bit of curl to these maple leaves. I haven't actually given them any curl yet. And then I'll go and design leaves for the rest of our trees. And then make some new ones that I haven't presented before. Okay, it's been many hours, and I've now finished every single kind of tree that I wanted to do. So I actually revamped the way that we draw the leaves using the Bezier curves. So instead of having a bunch of points and doing the generalized formula for the Bezier curve to get, you know, all these sort of weird shapes, it's really hard to make the exact shape that you want to do like that. So instead what I'm doing is I'm just having every set of 3 points make its own Bezier curve, and then the next set of 3 points will make another Bezier curve, and then again and again, so that it's a lot easier to make the complex shapes that a lot of leaves have. Whereas if we just did a bunch of points and then ran the general Bezier algorithm on top of all of of them. For some of the leaves, it's still easy enough, but for others, it's really hard. The more complex a leaf is, the harder it is to create it using just one large Bezier curve with many, many points. So that's what I've done there. So with all of that done, let's just jump into the final tree presentation. The first one up is this angel oak. So the angel oak is actually the name of a real tree. I thought it was the species of tree during part 1 of this video, but it's actually a specific tree. It's called a southern live oak, and the angel oak is in South Carolina, and it just happens to be a southern live oak that's really big. And we can do another generation 2 to try to get an even better one. Here we go. This one takes up a lot of lines, so it makes my computer laggy sometimes. But this one's kind of just a sprawling mass of trees and vines. So here's what it looks like in real life, and it's very beautiful. And next up is the pine tree. This one was pretty fun to figure out how to get all of the needles on it. So I just kind of set up a ton of tiny little branches that would all pop up out of the main branches and then sprout these little needles. So there we go, nice little Christmas tree. So sharp, so pointy. Next is the redesigned sugar maple. I revamped the maple leaf to look more accurate using that other Bezier system that I just talked about. So now I think it looks a little better. So there's that. I really like the red color of it. And here is a real sugar maple in case you're not Canadian. Here's another regeneration of it because I think it looks better than the previous one that we had. Next is the baobab tree. Now, honestly, this is kind of a goofy little guy, or big guy. You can find them mainly in Africa and Australia, and they have these really massive trunks with these branches sticking out of the very top. And honestly, I'm not even sure how these qualify as trees because it's obviously just a massive yam trying to pretend to be a tree by gluing on branches at the very top. I mean, just look at that. Look at that. Those are clearly glued on. It's not a real tree. Nice try, Africa. But it was fun to make. Moving on, next is the Joshua tree. These are pretty simple. They are a desert tree that grows in the Mojave Desert in the US. They don't typically have a lot of branches, and it just drew these little spikes on them to try to represent their spiny leaves. Here's a good picture of one right here. Next on the list is the acacia tree. Acacia trees tend to be pretty dense toward the top with this canopy of leaves going in sort of an umbrella shape, and their leaves are this little mini chain of tiny leaves that I modeled like this. So that is the acacia tree, and here is a picture of one in real life. And these guys you can also find like the baobab in Africa and Australia. Next on the list is the kapok tree. Now these guys I think are super cool. They are just massive trees. They tend to have large roots that you can see sticking out of the ground towards the bottom, and then a lot of them are different. They have some variety, but some of them have really long trunks with then a tall sprawling bush of their branches and leaves up at the top. Here's the picture that I used as a reference, and here's a good picture of their massive roots that you can see. And of course they need to be in order to support the whole thing. And you can find these trees in tropical parts of South America, like Brazil and the Caribbean, I believe. So that's the kapok tree. Very cool. Might be my favorite one. Next is the mangrove tree. These ones have kind of a simpler tree structure up top, but what their interesting part is the root structure down below. In real life, mangrove trees look like this. This is the one that I used as a reference. They have these roots going into the water, and they stick up and hold the main tree out of the water with this really interesting looking, almost candle-like design. So I thought that was pretty interesting. And you can find these guys growing out of the waters in Indonesia. The last of the real trees that I've modeled is the willow tree. Whoa, that's not right. Yeah, I actually had to hack it so that in order for all of the leaves to be pointing downwards to look like they're drooping down like a willow tree does, I actually have to hack my draw leaf function in order to force the direction that the leaves are drawn downwards. Because otherwise there's really no way with the setup that I have with the tree class in order to make them do it naturally through just an algorithm. So yeah, it's kind of a hack fix, but whatever. And then I just forgot to change it from the previous trees and had them all sticking out just now. But anyways, like I said, willow tree. This one I like a lot. I think it's very beautiful. For the leaves, they kind of have these long chains of leaves, and I would make them longer and have them extend even further down, but it really does take up a lot of lines to draw each one. So I just settled for a kind of medium-ish length chain of leaves. Here's a good picture of one in real life, and I'm actually not sure off the top of my head where these guys are from. Let me look it up. Europe, Asia, North America, and parts of South Africa, according to the tree trove. Okay, there you go. So that is the willow tree. And again, that's the last of the real life trees that I've modeled. I have also given some leaves to some of my fictional trees from part 1. Not all of them, but some of them that I thought would be fun. So the first one is this spiral tree. So I thought it'd be cool to give these little spiral leaves to it, and I'm not really sure what's wrong with this generation. It kind of looks like, I don't know, the Oompa Loompa haircut, you know, the purple ones. Let me pull up a picture of that. Let's see, purple, Yeah, kind of like this, you know? Wait, do they not actually have any purple Oompa Loompas? Are they all just like orange and green? Oh man. Well, there's some Mandela effect for you. Weird. Looks like we need some ethnic diversity in Willy Wonka's chocolate factory. Anyways, that is the spiral tree. Oh wait, I know where they were pointing down. Duh, because I forgot to take off the hack that I put on for the willow tree. There we go. All right, this is the spiral tree. Very, very nice. Next is the tree of life. This one is kind of just a big, bustling, honestly kind of an ideal tree, like the exact thing that you think of when someone says tree, and a nice sprawling root system too. I just decided to make this one because it's in a lot of ancient mythological and religious tales, so I thought it'd be cool to model it. So that is the tree of life. Very, very nice. And last but not least, we have the second tree that I added to the list that was not in part 1. It is fictional, and if you've seen part 1, you can probably guess what it is. Da-da-da-da! The truffula tree. I didn't think I could make a video about modeling trees without doing one of these guys, so here you go. It's mostly just a big dandelion with a giant puffball on the top, so it was, you know, the easiest one to model, but I still think it's pretty cool. So that's it for the tree generator. Again, if you haven't checked out part 1 already, definitely go do that, or you can check out this other video where I try to shove a Newtonian physics-shaped peg into a quantum physics-shaped hole, or you can just sit here and watch this massive truffula ball for a little bit. Alright, get out of here.